So David, it gives me great pleasure to welcome you. Thank you for your time today. I never thought I'd be able to introduce the Oxford Computer Consultants Professor of Artificial Intelligence and Machine Learning, but I'm delighted to be able to introduce you as that today. David, just a bit of background to you. So you're the Professor of Clinical Machine Learning in the Department of Engineering Science at the University of Oxford. You're a Research Fellow for the Royal Academy of Engineering, and you run the Computational Health Informatics Lab within the Department of Engineering Science, which has labs in Oxford and China. I'm delighted to see that you studied engineering in the Department of Engineering here at Oxford. My background is a mechanical engineer. My partner who I started the company with is a physicist, and we always tell the story that you can turn an engineer or a physicist into a software expert, but it's much harder to get someone to understand the application area to turn a software engineer into an engineer or physicist. So your research linked to this has resulted in patented systems for jet engineering, for jet engine health monitoring, and you worked on the Eurofighter Typhoon project. Since 2008, you've focused mainly on healthcare applications, and your current research is around the development of machine learning for tracking of health of complex systems. Your work has been commercialized by a number of spin-outs from Oxford University, including OBS Medical, Oxy Health, and Sensign Health. So David, welcome. What I'd like to do, we have 3 chats with you today. And in the first one, I'd really like to start with just a bit of an introduction to the field of artificial intelligence and machine learning. And it's going to be interesting to see when you use the term artificial intelligence and when you use the term machine learning. And that's something we'll be very interested in. So would you mind if we started with a few definitions? Because when I started in artificial intelligence back in 1980s, the technology was expert systems, which was sort of rule-based systems with inductive and deductive logic. How would you define artificial intelligence today?
I suppose I should start off with a quip. A friend of mine at a large software company, the second largest company by value in the world, I think it is now, says machine learning is what you call when you're talking to scientists, and AI is what you call it when you want to sell it.
Yes.
I suppose more formally, AI is a very broad church, and machine learning is a part of that. And you've, in your own background, obviously, you've got experience of a part of AI which isn't necessarily machine learning. So things like inductive logic programming and trying to discover theories and models about the world through reasoning may or may not come from machine learning. And so machine learning, perhaps a little bit more prosaically, is, I suppose clues in the name, teaching machines how to recognize patterns, maybe trivialized by thinking about it as presenting inputs to a machine and seeing what that machine, which is a trained model, can produce as its outputs. I suppose modern machine learning is even more complex, as you might expect. With growing computer resources available, we can have much more complex models than we had even 5 years ago, let alone in the 1980s, of course. So what it means to do machine learning is a big thing now, and hence, and what it therefore means to do artificial intelligence. And there's obviously a lot of overlap. As I've said, AI includes machine learning. And it's often hard to tell when one project is machine learning and when one's AI. Very often what we mean when we talk about AI, and you see it in the press, let's take some examples, an Economist article on radiography, on helping radiologists look at scans to identify areas of concern in a mammogram, let's say. That's classic machine learning. You're teaching a machine how to identify patterns in a codified structure which is based on the image. Whereas other aspects where AI has entered into our daily lives are in our social media feeds. We're being served adverts tailored towards people who are a bit like us, based on our patterns of use. So the same applies in healthcare also, which is the field where I do the majority of my research. Patients like me, what information have we got about an individual? Can we find patients who have similar information, and therefore can we make predictions about an individual or about the health of a system or about what advertisements a person would most likely respond to based on people who've had similar data?
That's very interesting, and we'll come back to that when we talk about some of the applications of AI in social care, which is an area we're interested in. I just wonder on that theme, has AI run into the danger of becoming a black box in some cases? Because when we had the expert systems, in the end, when there was an outcome, you could trace that back through a sort of a logic.
Yeah.
How difficult is the issue of the black box problem, if you like?
It's, in some senses, it doesn't matter. So, for example, if you construct a box that takes information about a patient and makes a likely prediction about what's going to happen, as long as you get that right to an acceptable degree, where an acceptable degree is something that medical science, for example, as a part of society that's very well codified for testing and diagnostic testing, is very well used to. As long as you're matching performance of your nearest predicate system, let's say, your nearest system that's gone for you, whether it be an actual drug or whether it be a human decision or whether it be a decision based on a box, then in some senses, that the distinction between a black box and a black box doesn't really matter. So, for example, medics are really used to using scores. Like when you're born, you get an APGAR score. When you later on in life, perhaps an elderly patient in an intensive care unit will get a different kind of score called a SAP score or an Apache score to predict what's going to happen to them in an intensive care unit. Because information is complex and people like to summarize information in scores. It's easier for me to talk about the health of a car in a single number than it is to give you the gory details of the 1,000 components in the bit that we're looking at. So humans really like scores. So if you can just show that your score is as good as the score you had previously, often that's good enough. But of course, that's not really satisfactory. And I guess where a lot of people, the difficulty here is that AI can fail in different ways to humans. So if a driver fails because in their process of driving, because of a human understandable reason, we can empathize with that, can't we? We can say, yeah, I get it, it was a human reason, and sure, there is a road death accidents number per year, and society is generally happy with that. Happy in the sense that we still allow people to drive, even though that number has existed for the last decade. But if a computer kills someone or has a problem, they typically do that in a very different way, in a way that a human can't empathize with. You think, well, no human would have confused the curb because there were 3 stickers on the road.
Yes, no.
So the scrutiny that a system, an ML machine learning system goes through can be very different and perhaps even a bit harsher.
Yeah.
Society is still working its way through that.
There's a first year philosophy exam question, isn't there? What's it called? The famous sort of tunnel, junction tunnel, the trolley problem, where if a human has to decide whether to go left or right on a track where there's a risk of an accident either way, what decision does it make versus the computer, and how do you? I mean, this is driverless vehicles, of course. We could have far more driverless vehicles on the road if the insurance companies could sort out how they're going to deal with the accidents. Right. That's what's preventing that. So it's fascinating problems. Thank you. And
just in terms of the explanatory component as well, obviously a big drive is, as our models get more and more complex compared to what we used to have, it's actual practice that we need some degree of explanation for them. So it's no good that computer says yes, in most disciplines. So along with increasing complexity of models, there has developed a parallel stream, and sometimes called explainable AI or explanatory AI, where, as you say, the decision can be explained to some degree. There are jargon terms for that, things like attention. So you can say, to what were you paying attention in this image when you said it was girl playing with frisbee? So canonically, the girl will light up when you highlight the word girl, etc. So there are mechanisms that you can build into these complex models to do that.
Yes, it's an interesting problem. It's interesting thinking about how the definition of AI has changed over the last 30, 40 years. Has it just changed to suit the convenience of the funding bodies, or is it because of the technology that definition has changed? I guess it's a bit of both, really, isn't it? But,
I'm always a bit skeptical about the rate of progress of AI in many ways, because although unrecognizable is the performance that we now have on certain tasks compared to what we could do previously, there's very little that's new under the sun, so to speak.
Of course.
And lots of the ideas that we're now developing in the context of these more complex models are ideas that you will have come across and be very familiar with from what we call good old-fashioned AI, expert systems and so on. So a lot of the first wave of neural networks in the 1990s had a bunch of really amazing thinkers, like David Mackay, the late David Mackay at Cambridge. He proposed things in his doctoral thesis which are still being used for, people are still digging out fresh ideas and fresh applications of these original thoughts. So not to demean modern machine learning, but there is a lot of very much reinventing the successes of the past in the context of the present.
Well, I think actually that leads me nicely onto one of my other questions, which was really about things like regression algorithms and Bayesian inference and other mathematical models. These lie at the heart of AI. So to what extent is AI a label attached to a mathematical discipline?
Well, it can be. So the joke is, if you're good at maths, you do Bayesian inference, and if you're not good at maths, you do deep learning. and that's merely based on the fact that to some degree AI can be commoditized. So you can be an undergraduate student halfway through your first degree, good understanding of maths, let's say, but perhaps not the most detailed understanding. You just a couple of years out of high school, and you can build deep learning models pretty quickly. You can take data, you can get models, and you can get results. And it's relatively easy to automate some of that process because there's, as you can imagine, there's not a lot of prior expertise that some of those models would rely on. So there's a lot you can automate. There's a big field at the moment in auto ML. How much can you do without a human in the loop? How much of that basic modeling process can you do? But it's a bit like fixing your car. I'd much rather have someone who really knows how a car works building or fixing or maintaining my vehicle than me trying to do it myself if I don't have that expertise. So in modern machine learning, where the models are so complex, trying to do that without a background in maths and computer science is a recipe for disaster. Why would you do it?
It reminds me of a very interesting project we did for the Ford Motor Company for their apprentice trainees, and it was a multiple choice test to look at whether they'd understood the principles of how an engine functioned. And there were three elements of the question. So there was the question itself, what is a carburetor? Right. Then you had to give your answer from a list of multiple choice. You had to say how confident you were in your answer. And then you had to pick a reason for your answer and confidence. And the worst thing you could be was wrong and confident. I mean, that was a disaster. If you were wrong and not sure,
understood.
That's fine, you could be retrained. But what you didn't want, and I think that's a really interesting principle actually, this danger of almost back to the black box question of people reaching the right conclusion for the wrong reasons, and then you're into a lot of trouble.
So I would say, particularly in safety critical AI, where it really matters, a handling of uncertainty in exactly the way you've described is very, very important. Otherwise, you end up with a machine that is 100% confident no matter what it does. You're essentially putting a gun to its head and saying, you must make a decision, even when you don't know what you're doing, so make that decision, please. Whereas a more mature, robust machine learning system will, as you say, will recognize its uncertainty and propagate that through to its output and tell someone, and hopefully the system that has been constructed to incorporate that understanding of uncertainty. So if a machine says yes, but high degree of uncertainty, then that decision with its corresponding uncertainty is taken into account when you're combining that to make decisions further downstream.
I mean, we've seen this with the R number, haven't we, during COVID? The government just about felt they could trust the public with one number. The idea that they might give a probability distribution around it was we weren't going there.
Indeed.
And that was really quite interesting to see how little confidence people have in public's ability to understand any sort of certainty and confidence on numbers.
I think we're all epidemiologists now anyway.
Yes, we are, aren't we now? So just sort of on that theme, therefore, of these tools, because a number of companies now, Microsoft, Azure, and so on, they offer these AI out of the box techniques and tools, including for machine learning. Have you seen people successfully build applications and deploy them from that basis? Have you?
Yeah, absolutely. I mean, they exist for a reason. Microsoft is populated full of smart guys who are doing things for a very good reason, as one of many examples. I would say probably, just harking back to that previous point, that what's useful there, what's most useful is bootstrapping and speeding up the process for a machine learning engineer. So if you've got a data scientist or team of data scientists in your company, just reinventing the wheel for every new project may or may not be necessary if it's a fairly well-trodden path. So if it's a well-understood problem, why not get some help and accelerate that process by automating some of the more mundane parts of the pipeline? So I buy that. And machine learning, one very reasonable application of machine learning is just automating the boring stuff, whether it be judges' decisions, at a magistrate level, a very low level of courts, automating that process, whether it be automating the boring bits of radiography, as radiographers describe it to me, like looking at the scans. There's a lot of donkey work that can be done by machine learning quite quickly, freeing up humans to do the intelligent stuff. I would totally agree that's it's got its role to play. Would you want to rely on it for an enterprise level solution without having somebody who knows what they're doing, checking the outputs and validating and verifying? I don't think anybody would go there.
I wanted also just to ask you a little bit about your research interests. I kind of would like you to answer that in two parts. One is your current research interests as driven by funding bodies and the organisations you're working with, and perhaps the other element of it being, if you were to start a new PhD, what would be your research interest?
Oh, that's a really good question. Thank you. So to answer the first one, I think we're very lucky in the sense that, so my interests are in healthcare applications of AI and developing new approaches in AI that are prompted by the very special limitations and constraints that you get in healthcare, which may not be replicated in other sectors. There's not very many people who do AI in healthcare, particularly for non-imaging data, which is what I do. So things like sensors and genomics and hospital data, all that sort of stuff. So because there's not a huge amount of activity there, funding councils, I have to say, are really supportive, and I'm very generous for the support of the funding councils in really handing over to the academics to come up with a vision. And so, in some disciplines, it's definitely the case that there's a steer, isn't there, by where the money is, and research might follow the money. But in many cases, in modern research within the UK, particularly in EPSRC, which is a physical sciences funding body for people like me, it's very much more the other way around. The money will go where there are good ideas, which I think is the right way to spend public money. Good question about what would you do if you wanted to do it the other way around. I always said I wanted to study classics, actually. So, and I ended up as an AI student. So you never know.
Okay.
Perhaps the intersection of the two.
All right. Well, you've dodged my question because I kind of wanted you to tell me what you might research if you were doing a PhD in AI. So, I think if I were starting again, the bits that are most interesting to me at the moment are how computers learn. So let me just qualify that fairly woolly statement. As data sets get more and more massive, and therefore models get more and more massive to compensate for the complexity, and because that degree of complexity is enabled by the data, whether it be imaging data or whether it be patient data or social media data, whatever it is, it begins to pass the point where humans are in control of the entire process, or have a mental understanding of the entire process, in the sense that when a system has got several billion parameters, the human can understand the architecture, the human can understand the dynamics of the problem, but one rapidly starts to lose the nuance of how this machine is behaving with individual classes of entity, because there are so many of them. And in my field, for example, if you do a clinical trial of 200 or 300 people, and you've got time-varying data for those patients, you can look at that 300 patients worth of data, and you can build models that correspond to that understanding. And it's a very intuitive, one-to-one understanding. The designer has full control and understanding of what that model is doing. You scale up to 2 million patients, and you rapidly have to admit to yourself that you cannot any longer look at all the input data, and that degree of human understanding must be suspended. And
you become slightly abstracted from the input data because the input data is so vast.
Yeah.
So we're developing in machine learning now. A really exciting focus is in meta learning or other. We've got many names, but it's basically AI to help AI to help humans train AI models in that sense. So how do we best construct these very, very complex architectures, which might otherwise be trial and error? How do we do that with the guidance of an artificial intelligence?
And how do you pass the third bit of my test? You can tell me how what the answer is. You can tell me how confident you are, but how do you pick the reason so that I know you understood the question? That's
quite so.
And that's. I mean, we see this in financial markets, don't we? With systems running the financial markets and humans no longer understanding what happens, and you get herd behavior. Maybe that doesn't matter so much in artificial intelligence. Herd behavior is a good thing. It suggests everything's heading towards a common.
Well, in that example, there are examples, aren't there, of stock market crashes?
Well, exactly.
Of nano trades following one another down into an optimum.
But I mean, would machines all start following each other down the wrong diagnosis? I mean,
Do they start to? Yeah, absolutely. Do they all start to fail in the same way? Absolutely. So, how you protect yourself against catastrophic failure is also extremely exciting. So, I think that's another really important thing about the application of AI in the real world. It's not very sexy, actually. So it's not a very sexy thing in terms of if you're doing research on AI, what you want to do is say, I've got the best performing artificial intelligence model for doing task X. It's a different proposition to say, yes, I've got this artificial intelligence system that nurses are happy to use and that medics are happy to use, or which is being used by meteorologists on a daily basis, whatever it might be. So that degree of reliability engineering and that degree of making it sufficiently robust for humans to depend on it is another discipline in AI, which is often not recognized. In safety critical systems, it's a big deal, isn't it? You want to avoid the catastrophe. I always like to say of a medical system, if the medical system fails, so to speak, one time in 20, it's going to get used 0% of the time.
Quite. Look at the AstraZeneca, fuss over the blood clots, one in a million, and look how quickly that gets abandoned.
Indeed.
I don't agree, by the way. I think AI is a sexy field. I mean, I think when the classicists organise the dinner party, you will be up at the classicist end of the dinner table. It was the same during the dot-com era. So when the dot-com boom came along, Kaz and I, we were suddenly moved up. We were no longer down with the accountants. We were moved up, allowed to talk to the classicists and the historians and so on. And then, of course, there was the crash, and so we were sent back down to talk to the accountants and so on. But the only difference is the historians and classicists wanted their money back. But David, thank you very much. That was an extremely interesting set of answers, and thank you for your time on that.
Great pleasure.